if we're all good to go.
You haven't shared your screen?
Yeah. Setting it up right now. Trying to, what was it? Set it up so that I get presenter mode and you guys get a full screen view of a slideshow. All right. Do we see a slideshow?
Right.
Awesome. Good to get going?
Yeah.
Sweet. Well, thanks for coming to maybe my second, maybe third Heist Talk. First since I've left the University of Arizona. Hi, everybody. I'm Jaren Ashcraft, and I'm back to talk to you once again about polarization aberrations. The title of this talk is taken from a JADIS paper that recently got accepted, which was very exciting, based on some work that started in 2023 and continues to sort of be relevant to some of the work I'm doing as a postdoc. So just for those, but before we get into all of that, just for those who are out there who have forgotten that I exist or never knew in the first place, because ultimately everyone fades into obscurity. Aloha, I'm Jaren. My defense was almost a year ago, last April on tax day. So have one of my favorite photos ever here on the left of everyone surprising me in poke shirts, which was fantastic. And my advisor was Ewan Douglas, who's shown here on the right during our graduation. He later hit me with the balloon that's in his hand. So that's been exciting. Oh, whoops. I had an animation on that, I guess.
I think the balloon is
Current.
still in our office too.
Oh, that's wonderful. Yeah, that's good. I'm glad the balloon's still around. I'm currently a NASA Hubble Fellow, specifically the Sagan kind of exoplanets flavor at UC Santa Barbara, working with friend of UASAL, Max Miller Blancher. I've brought the tradition of ice cream, so every time I go back there, I buy everybody ice cream at a wonderful place. The ice cream game in Santa Barbara is truly amazing. Um, but I live full time in Hawaii, where I'm at right now. We can talk about reasons for that if anyone's interested, but that's just kind of my situation. And now we can head on back to the research talk that sort of covers high contrast imaging, how polarization aberrations can limit high contrast imaging, and what it means for chronographic imaging of habitable worlds in the coming decade. First, just kind of a brief introduction to polarization and high contrast imaging, or how detecting light wiggle, or the direction light wiggles interferes with our goals to find aliens with strategic light blocking. Those of you who were there may remember this diagram from my thesis defense. This is kind of what solar systems tend to look like, or certainly what ours does if you were to ride the magic school bus. We have these rocky, tiny inner planets where we live, and large gaseous outer planets, and a bunch of other stuff like dust, comets that zip in and out of the system. Well, once upon a time, someone dared to ask the question, like, "Oh, hey, are we the only form of, sentient life in the universe?" And the answer, yes or no, both of those have profound impacts on, the future of astrophysics. And so people sought out to start detecting exoplanets. Many of you may be familiar with this figure from Kat Follett's 2023 kind of review paper, but this is a plot of basically detected planets as a function of, on the vertical, how big the planet is, and on the horizontal, how far it is from the host star. The colors denote the detection technique, and I want you to look at high contrast imaging. That is the confirmed high contrast imaging targets are for very, very big planets that are very far away from their star. So they're very bright and like relatively easy to detect. Whereas the sort of Earth-like analogs are far from almost every detection method on this graph. So finding exo-Earths is very hard. But we want to do it with direct imaging so that you can very conclusively see the planet is there and then isolate the light for spectral characterization to identify chemical species that would indicate it supports life. How we do that is with a telescope. Unfortunately, we don't have a magic school bus and we can't just drive over to the nearest, I don't know, exoplanet and go look for it, like we would see on the left. What a telescope actually sees is on the right. The consequence of light being kind of wave-like means that it diffracts, and so light from the star will spread all over your focal plane and be many orders of magnitude brighter than your planet. On this plot, I've plotted a relatively bright planet, so depending on screen resolution, you might be able to see it. Um, but if you wanted to actually parse that planet from the starlight, you use something called a coronagraph. You focus the starlight onto an opaque mask called a focal plane mask to literally punch it out. And then, because diffraction happens, you need an undersized pupil stop called a Lyot stop to block the rest of the starlight. And if we kind of do that for a simple Lyot type coronagraph, we see that the exoplanet will sort of jump out at us, plain as day, which is really nice. It passes through the coronagraph more or less unvignetted. Um, I'm particularly interested in kind of my research activities and certainly in kind of the end of grad school in understanding how polarization and coronography work together. Now, polarization can mean a couple different things. When I say polarization, I'm talking about the direction the electric field of light is wiggling. The electric field is the easiest to detect, or much easier to detect than the magnetic field, so that's typically what we're actually measuring when we have light incident on a detector. So we define it as the orientation of the electric field vector. Polarization has been used in high contrast imaging to do very exciting science. This is one of my favorite plots I've ever seen by Miles Lucas, who's soon to be brass instrumentation fellow at the University of Arizona. So he'll be hanging out with you guys pretty soon. He's a very good buddy of mine, current, soon to defend kind of PhD student at UH Manoa, and single-handedly upgraded the Skexeo Vampires instrument, basically. He kind of led that effort. And he shared with me what you can do with polarimetry behind a high contrast imaging target by looking at the difference in orthogonal linear polarizations. You can see debris disks kind of pop out very readily because they're very polarized signals after your, signal propagates through a coronagraph. So polarization can do some really awesome things for us in high contrast imaging. Unfortunately, the spatially varying polarization state can also limit our detection of exoplanets. Here's a figure from John Criss' 2019 integrated modeling paper on the Habex coronagraph, showing that polarization aberration, showing up in that middle column, predominantly degrades signal at the inner working angle. So polarization aberration, while it can help us, can also limit detection right at the sensitivity limits of a coronagraph. When we describe polarization aberration, we use something called the Jones pupil. This is very simply a Jones matrix evaluated at every point in a beam as it propagates through a telescope. The Jones matrix is a 2x2 matrix operator that operates on the polarization, or the electric field vector, projected into two orthogonal coordinates, and it tends to look like the map on the right. For those of us in the room, including virtual attendees that have to wear glasses, telescopes, perfectly aligned, perfectly polished telescopes, also have astigmatism, not unlike our eyes do. And the insidious thing is that if we look to the right, on the on diagonals of the J00 and J11 kind of phase maps that are the two right columns, the astigmatism signatures are of opposite sign, so they can't be corrected with traditional adaptive optic systems. Unfortunately, for us, next generation telescopes are going to be amazing and be incredibly sensitive instruments and do really transformative astrophysics, and all of them have direct imaging as a science goal. Unfortunately, owing to their sensitivity, all of them will experience polarization aberrations that degrade signal at the inner working angle. And so, when I was in grad school working with a lot of you in the room, we asked this question: how do we model these polarization effects so that we can understand their impacts and then hopefully design methods to compensate for them? I created this Python package called Poke, which is basically just came out of all of the code I had to do to pilot the Zmax and Code 5 ray tracers using Python for the various integrated modeling efforts we were working on. And it allows for the kind of direct connection of commercial ray tracing engines like Zmax and Code 5 to open source physical optics modeling tools that we use like Poppy, HCIPy, and Prism. And so, given that we built this, we wanted to apply it to NASA's Habitable Worlds Observatory. And this is where we begin to talk about something called the 6-meter Space Telescope, or 6MST project study, as I like to call a precursor to NASA's Habitable Worlds Observatory. you see, the Astro 2020 Decadal Survey recommended a 6-meter infrared optical ultraviolet flagship telescope to detect and characterize 25 potential habitable worlds. And to do so, you need a coronagraph in order to directly image them and then characterize or send that light to a spectrometer or IFU to directly characterize them. In advance of the decadal survey, the HABEX and LUVOIR missions were kind of mission concepts were proposed. HABEX had a couple different mission architectures, as did LUVOIR. Here we have kind of the HABEX variant that included a star shade that was an external occulter as opposed to using an internal coronagraph. And on the right, we have LUVOIR, which has kind of the LUVOIR A centrally obscured hexagonally segmented architecture. And so both of these studies really sort of fed into what happened after the decadal survey made this recommendation. You get one telescope and it's got to be 6 meters, basically. Um, Polarization aberrations and the 6-meter Space Telescope Project study are relevant to HWO because immediately in the aftermath of this recommendation, NASA JPL did kind of like this warm up of we're going to try and design a 6-meter space telescope that is suitable for habitable worlds. And in 2023, I sort of got in contact with the folks that were working on 6MST to answer this question. Can polarization aberrations be mitigated by splitting the coronagraph into two orthogonal polarization states? I.e., there's two onboard coronagraphs sitting behind a polarization beam splitter. One sees X polarization and one sees Y polarization. The hope is that this would clean up the signal that corresponds to that, like a differential astigmatism. Your aberrations for orthogonal polarizations are of different sign. So the wavefront control problem becomes easier if you have one polarization going to one arm and one going to the other. And so we sought out to model and quantify this. This is what the 6-meter space telescope looks like. It's an off-axis, hexagonally segmented telescope whose segmentation is based on the Ultra Stable Optical Research Telescope, or USORT, which was a different kind of study. And it has this one onboard coronagraph with a fast steering mirror, two deformable mirrors, one out of pupil for amplitude control, and multiple places where you can put in pupil and focal planes. This actually directly evolved into the exploratory analytical case 1 design for Habitable Worlds Observatory, which is kind of a precursor design, or I guess a pre-precursor design instead of the 6MST's pre-pre-precursor design. For those of you working on Habitable Worlds Observatory, it's very similar to EAC1. Unfortunately, we had to take a bit of a sidestep, which was very exciting, because there wasn't a coronagraph designed for this telescope yet. And so we had to make one, and making a coronagraph that achieves exo-Earth level contrasts is difficult. That's a non-trivial problem, especially if you didn't want to use kind of mathematically ideal coronagraph operators and wanted to go into this next level of fidelity where you are like, okay, let's get a coronagraph that we could actually build, right? And so we go on this little side tangent. And now we begin to discuss algorithmic differentiation. This is a topic I bring up a lot since doing this study because it has considerably accelerated my research. This is kind of a figure I show every single time I bring up algorithmic differentiation as a little warning that I'm going to get on a bit of a soapbox here. But algorithmic differentiation is a very powerful tool that's enabled a lot of modern research. How it kind of works is that you write your forward model into your computer that describes some scalar loss function. So in coronagraph design, say you want a dark hole of a particular shape. Your loss function would be a literal, like physical optics simulation that propagates your light to your coronagraphic focal plane and compares it to the kind of shape of the point spread function you want. You want it to have a high contrast region somewhere. And using backpropagation rules or ways to propagate the gradient of your loss function back to your input variables, you derive the adjoint model. Now, this is relatively easy in the implementation. Conceptually, I found it difficult when I was first doing this. Um, but this kind of algorithm, it was actually the kind of key enabling, one of the enabling kind of algorithms behind the 2024 Nobel Prize in Physics for foundational discoveries and inventions that enable machine learning, because this is exactly how like AI neural networks are trained, is using this backpropagation algorithm. When we derive this reverse model, we call it algorithmic differentiation or algodiff. And so using the forward and reverse model together allows you to do really fast and efficient optimization in order to design things with millions of parameters, like a coronagraph mask. There is another kind of flavor of doing this called automatic differentiation, where open source packages have actually implemented these gradient backpropagation rules for you and interpret your forward model and create a reverse model for you. And I call this automatic differentiation. Some of the Python packages people in this group may be familiar with that do this are JAX, TensorFlow, and PyTorch. And they do make it really easy. My Katsu kind of Mueller matrix polarimetry simulation package has a hot swappable JAX backend that you can call just a function that says set backend to JAX, and then all of a sudden you enable automatic differentiation. But it tends to be a little slower than implementing it by hand, which is strictly more efficient. So that's what we elected to do because chronograph designs tend to take a lot of time. Using this, we derived the reverse mode algorithmic differentiation model for Apodized Pupil Lyot Coronagraphs. And to my knowledge, this is the first time people have done this. A lot of APLC design before has either been done using kind of bigger computer diplomacy as the solution, where just throw it on the biggest possible computer you can and use finite differences to optimize, and it takes forever. Or I think Emil Poor published in 2022 SPIE proceedings a kind of TensorFlow version of HCIPy that uses automatic differentiation to do APLC optimization. The forward model is shown here in math, but it's just enforce your inputs are real, propagate to your focal plane, apply the focal plane, propagate to your pupil plane, apply the Leo stop, propagate to a focal plane again, compute the intensity, and compute the mean squared error with respect to your desired dark hole. And this was just a sum over the squared error to try and minimize the contrast as much as we could. The reverse mode adjoint model is derived from just looking at each of these steps and then looking up the kind of backpropagation rules that have been derived for us already. A very convenient table is in Jerling and Phenup 2014, where they derived a backpropagation model for phase retrieval, and that's what I used as my reference. And if you implement both of those into a nonlinear optimization scheme, you have your difference in image with respect to your target dark hole, and then the gradient model, and then you pass that to a nonlinear optimizer like LBFGSB and let it go. And we did this sort of in polychromatic space of at 5 wavelengths so that the coronagraph had a 10% bandwidth with kind of large inner working angle or a 3.5 lambda over D nominal inner working angle and like a 2.5 lambda over D inner working angle. And these are the designs. And one of the kind of big benefits of using this artisan hand-rolled algorithmic differentiation was that each of these designs took like 45 minutes to generate on the HPC, the Puma cluster at U of A, which is kind of record-setting in terms of APLC design. We didn't advocate for that too much because there are a lot of things we were ignoring, like trying to make these binary solutions, for example, which is how you actually realize an APLC. But we called this good enough for a chronograph operator in order to compare polarization aberrations. In evaluating the chronographs, the throughput's not great, but it's not noticeably worse than other Apodized Pupil Lyot coronagraphs. We see that the plot on the left here, we get like a 20% core throughput, slightly over, for the 3.5 lambda over D inner working angle and like a little over 10% core throughput for the 2.5 lambda over D inner working angle. And this trade of inner working angle with throughput is pretty well known. So it was something we expected. And then the contrasts nominally get to like 10 to the minus 11, so we called it good. Now, going back to kind of the title, we wanted to compare polarization aberrations from existing mirror coatings and how they affect coronagraphic imaging. We nominally decided on these three mirror coatings and would vary the coatings on the like primary, secondary, tertiary, and quaternary mirrors, the first four mirrors in the 6MST kind of ray path. and compute the polarization aberrations for ELIF, which is a coding that people are very excited about to enable ultraviolet science for HWO, a Hubble Space Telescope-like coding design, which is just something that's been in space before. It's literally the formula they used for HST, and a protected silver coding. This is not particularly optimized for space-based payloads, but it has more dielectric layers, and we were curious to see the influence of that, because it's a very different coding from the other two aluminum-based codings. If we look at their nominal polarization aberrations, the diattenuation, or like the polarization, how much it's like a polarizer, and the retardance, or how much it's like a wave plate, as we show on the left and on the right, respectively, we see that the ELIF and HST coatings are pretty large diattenuators, relatively, with respect to protected silver. This is in the visible near at like 656 nanometers. But the Hubble Space Telescope is the greatest retarder, so it's the most like a wave plate as a function of angle of incidence. And we were sort of interested in understanding that effect. If using a physical optics model, we propagate using these chronograph designs the polarization aberrations to the focal plane. This is sort of the nominal contrast degradation you get. And interestingly, we see it's very directional. Also interestingly is that that direction, providing I synced up the coordinate systems right, is actually the kind of off-axis direction of the telescope. So we see larger degradation in that direction than in the other way, which I thought was kind of a nice sanity check about kind of the geometry of how polarization aberrations arise. And we see that nominally, the protected silver coating all the way on the right performs the worst. It has the largest nominal kind of focal plane degradation. But we wanted to assess how much the split coronagraphs in wavefront control matter. If we look at the radial profiles, we see exactly what we saw in the previous plot. The protected silver is really bad, and then the kind of HST coding, and then the ELIF coding. So the ELIF, which is the one that people are most excited about, is actually performing the best, which was encouraging. But this is without any compensation of the Jones pupils and any polarization splitting. If we correct the mean, amplitude, and phase error after splitting the coronagraphs into X and Y polarization, we can see considerably less degradation. So this is for the X polarized channel. And I want to draw your attention to the like dashed line. That dashed line is sort of the nominal contrast of an exo-Earth, an Earth-like planet at 10 parsecs with an angular separation of 100 milliarc seconds. So this is the 10 to the minus 10 number that people throw around. And we're well above that, particularly at the inner working angle, before the compensation technique. And after, we're far below. So this is one of the studies that sort of enforced the idea that polarization splitting, or splitting the coronagraph into orthogonal polarizations channels is a valid way of, compensating for polarization aberrations, because it basically disappears. And interestingly, we see this in the Y-polarized example as well. The HST coding has the worst residuals, whereas what is it? The protected silver, the blue, and the ELIF are sort of comparable in performance. And if we go all the way back, I forgot to include this as a follow-up slide. We see that trend directly relates to the retardance, the plot on the right. The Hubble Space Telescope was light coding was the greatest retarder, and that resulted in the kind of worst contrast degradation at the inner working angle. So we see that retardance tends to predict coronographic performance, and that can influence further thin film design studies. So you don't need to include a whole physical optics propagation routine in your thin film optimization, which is computationally expensive, as I know people in this column now. But you can just minimize the retardance of your coatings, and that will give you suitable coatings for chronographic imaging of habitable worlds. In the future, and something that I pitched to work on in my postdoc and have been doing for kind of the past couple months, is to integrate these physical optics models of kind of HWO-like coronagraph models into exoplanet yield calculators. So there exist tools like Chris Stark's altruistic yield optimizer and Savaronsky and Morgan et al.'s. I know there's a bigger sort of contributor to exosims. Sorry, they're library exosims. They allow you to simulate a design reference mission and optimize it to maximize the kind of statistical number of exoplanets you expect to detect, which is great. And because polarization aberrations are such small signals, it means that you can leverage astrophysical degrees of freedom, like your integration time, how many times you go back and revisit a given planet, to optimize your detection. And we have some preliminary results that we're hoping to submit to JADIS. Here's a kind of digested histogram of the exoplanet yield data. On the left is a histogram of how likely you are to detect an exoplanet around a given extrasolar system as a function of the frequency, right? And we see that overall, this is for a charge 4 vortex mission, polarization aberrations reduce your detection likelihood across the board, reduce the total number of detections you can get, and kind of shift it to the left. So more systems are less likely. It also increases the required characterization time by, I think the median characterization time increase is about a day. You can see the sort of, you'd be hard pressed to call that curve a Gaussian, but the sort of distribution shifts to the right to being longer. So these effects do have a consequence, negative consequence for observations. But we found in results that, we're still reviewing to make sure they're high fidelity, that for higher charge vortexes, like the charge 6 vortex, and generally coronagraphs with larger inner working angles, you get the astrophysical degrees of freedom are more than sufficient to compensate for polarization aberrations, and you get a negligible degradation in yield. So it's only these really like small inner working angle sensitive coronagraphs that we expect it to actually be a problem for. We've also been kind of continuing the chronograph design study because the APLC design algorithm we proposed in this paper was very efficient. We can crank out monochromatic designs in like a couple minutes. And so I've been working with my old NSTGRO mentor, AJ Riggs, on APLC designs in part to support the Black Silicon SAT, CC Emery Jenkins, if you're still working on that. And I have actually found a way to make the solutions more binary, and it's by adding a core throughput optimizer, which we hand-derived the forward and adjoint model for. It doesn't increase the runtime considerably, and we're able to get pretty high throughput and 10 to the minus 10 designs that look functionally binary, as shown on the left. Now, this is monochromatic. As it turns out, when you go to broadband and try to optimize core throughput, it's way harder. And so that's something I'm still trying to understand. But this is something that will hopefully have direct implications on UASL research going forward. And that's the end of my talk. Thank you very much. Do we have any questions?
Jaren, I have a couple questions actually. So,
Yeah, what's up?
yeah, so my first question is just to put it in some more context. I mean, how does the level of contrast degradation from polarization aberrations compare to the type or compared to like the amount of contrast degradation you would affect or you would see from other like more typical aberrations like other like low order or high order aberrations that like is this big compared to those or like do we need to worry, should we really be worrying about all of those or making sure that all of those are also perfect so that we can get to the level of contrast that we want?
Yeah, so that's a great question, Justin. Thank you for that context. The answer is that the polarization aberrations completely, like even without taking out the kind of scalar wavefront error component, only end up being like a nanometer to RMS. So they're pretty small. They're also of low spatial order. They look like these astigmatism terms. So coronagraphs are already pretty insensitive to them. They're really, really very tiny. And they may have been a problem for the Roman coronagraph at those contrast levels if the hybrid Leo coronagraph, which has a 3.3 lambda over d inner working angle, wasn't at a polarization aberration null, which John Crisp reports on in his like 150-page long integrated modeling paper for the Roman coronagraph. The only problem, because the cumulative optical surface errors from in both phase and amplitude are going to be way bigger. The residual jitter and kind of misalignment based aberrations are probably going to be bigger. Um, but they can all be compensated for. with a deformable mirror. If you have a deformable mirror in the system, you're good. You can take care of them. Not, not to make wavefront sensing and control sound trivial, but there is a solution. Whereas with polarization aberrations, despite a small amount of wavefront error, you never achieve a null. There's a balance between the two orthogonal polarization states, but it never goes to zero. With two deformable mirror wavefront control, you can get to zero. And that's what's insidious about it. I didn't include it here. I may actually have an extra slide on it. I don't think so. I have stuff about Grommet in here. I don't think so. I'm submitting an APRA with some folks to actually use metasurface polarization optics to act like a polarization aberration compensator in the way a deformable mirror does. And so there are some technologies that you can use to clean it up so it isn't even a problem. But it's a small source of wavefront error that's just annoying because you can't put it to zero.
All right, cool. Yeah. The other question I had was, and I'm not sure how much you know about this, but since you showed a star shade, I was curious as to whether or not star shade designs suffer from similar types of aberrations or have these types of problems as well.
Star shade. So I don't believe they do. I think star shades are as a non-star shade expert, um but one who spends a lot of time about thinking how polarization aberrations arise. The reason polarization aberrations are bad are because they mess with your occulter. So they cause light to spill off that focal plane mask and propagate into your dark hole. And so that's bad. But if your occulter is outside your telescope, your light's already 10 to the minus 10 by the time it passes the star shade. Now there's a higher, so that's like the first order effect, is that star shades should be pretty immune to this. Interestingly, when you try to demonstrate them in the laboratory, you have to scale them down such that you get waveguide coupling effects at the very petals of and so it's like a different kind of polarization aberration, which is weird. But there is a higher order effect where the polarization aberration will couple into the speckle field that the wavefront sensing and control algorithm needs to deal with. Now, though the like relative presence will scale with the amplitude of the speckles, which is already way lower. So that may not be a problem, but it has the ability to like complicate wavefront sensing and control solutions. But that's common to both a coronagraph and a star shade. So star shades are strictly more robust to polarization aberrations as far as I know.
Cool, thanks.
Spot of
I have
Virago
a,
engineering is pretty correct.
I have a question on how you've been designing the APLCs. So
Yeah.
do you just let LBFGS run for 45 minutes, or is it like it's broken up into control iterations where like it solves for one solution and then the next and then the next, and it inchworms its way to the final solution?
A good question. So, the answer is functionally letting LBFGSB run. Um, specifically, I pass LBFGSB the forward and adjoint models to give it an analytic gradient, and I tell it how many iterations I want it to go to, and it will go that many iterations. You can define like an exit condition. I haven't done that, and the answer is kind of GPU go Brrr. It doesn't take very much time at all to sort of workshop the monochromatic solutions. It takes a couple minutes to just run. And so I haven't gotten any more sophisticated than that. You can play a couple more games with how LBFGSB is implemented. One of the things I'm leveraging is it supports exact box constraints, so you can constrain the input values to be 0 to 1. But you can also kind of take the pupil apodizer mask solution out, do some additional kind of refinement on it. So there's like a projected gradient descent technique that's sort of interesting, where given a generally grayscale solution, you can project it onto a binary solution and then give that back to the optimizer and have it do another iteration. It will return a grayscale thing that you then make binary and then pass it back in. And so that's way slower, but it is a really good way to enforce binary solutions.
Is that how you generated this binary one?
No, not at all.
Oh,
This one I
okay.
just let go for 24,000 iterations, and with a core throughput optimizer in addition. So if you just optimize for core throughput as well as contrast, the solutions are naturally binary, which is
Oh, that's
very
cool.
interesting. I had no idea about that. I just assumed that people were like, no, no, I want a binary solution, so give me a binary solution. But it's frequently better to not do explicit constraints on the thing you want, in terms of optimization. There's usually an indirect and like more a better way to do it in terms of convergence. And so this is a way of being like, oh, binary solutions just have better core throughput. So if because core throughput is a very smooth thing, and
Intuitively, that
binarization
makes
is not.
sense.
Yeah, right.
Right.
It's like, oh, there's more open space.
Yeah.
Um,
But
but
why
it
LBFGS naturally goes to a binary solution for core throughput constraint, that's not intuitive.
no, no, not at all. Right.
Yeah.
It's just something like people, the community TM has discovered, and it's like, oh, when you so this is how the Roman flight masks were designed grayscale, but with a core throughput optimization that made them what is it, binary. And part of what's helping is that in contrast to the coronagraphs I designed for the 6MST study, which just have an opaque spot, using an annular focal plane mask limits the number of spatial frequencies that propagate through your system. Which means that you can have like slightly grayscale binary solutions at really high spatial frequencies and then just clip it to a binary solution, and it won't affect your chronographic performance all that much. And that's kind of how AJ did it for Roman.
Hmm.
So it's I don't know, optimization is really weird and very kind of like it's very much feeling like more of an art than a science. You just kind of have to like know and feel it out, which is interesting. But
So
so it's kind of addicting.
how many iterations did you actually let LBFGS run when you said it took 45 minutes?
Oh, this one? So this one was considerably less efficient. So this was 3,000 iterations.
Oh, wow.
Um, because I had, and something I didn't realize when I was doing this, so for all of you who end up designing coronagraphs, if you have a dot versus an annular occulting mask, it means you need to model very high spatial frequency content in order for your diffraction model to be accurate and to not have like errors propagate to your dark hole. So for not that much focal plane sampling in terms of like field of view, I could never get to 10 to the minus 10 contrast. And as I increased like how big my focal plane was, I could get there. So my focal plane was like 4096 elements, but with the annular focal plane mask, everything else is zero. So this one I mentioned took 24,000 iterations. That also took 45 minutes. But the focal plane was way less sampled. It was like the same resolution, but it was like I don't know, like 256 elements instead.
Hmm.
So annular focal plane masks for APLCs are way easier to design because you don't need to account for all of the high frequency content. It's one of the reasons like vortexes are really hard to model because you need to sample the like crap out of them,
Yep.
both in field of view and resolution at the singularity. So it's interesting.
What if you have like just a more powerful computer?
Bigger computer diplomacy is always an option. But I mean, one, that's expensive. Two, environmental degradation. So, efficient algorithms are green, and save the planet because GPUs go burr, it takes a lot of power. And the more efficient your algorithm is, the more of a parameter study you can kind of do on bigger computers. So your algorithmic gains always scale with your computational gains, right? So if something takes an hour on a GPU or sorry, an hour on your like MacBook and then like 10 minutes on a GPU, I'm pulling these numbers from nowhere. That's like what, it's a factor of six or something. You get the same factor of six going from like 10 minutes to whatever 10 divided by six is. And being in that regime of things taking hours versus things taking minutes is huge for productivity. So, what we're trying to do is actually, since this is for the Black Silicon SAT, if this turns into anything, who knows if I actually learn how to successfully design binary APLCs. We're probably just going to run it on the biggest computer that between AJ and I we have access to and just brute force optimize for a bunch of different focal plane mask solutions and Lyot stop radii, the best coronagraph we can get. And then just out of all of those, choose the best coronagraph. And that's partially enabled by the fact that um, uh, the algorithm's efficient. And so you can only do that and have it not take literal days if you have efficient algorithms. And that's why automatic and algorithmic differentiation are great.
I wonder how much like GPU power we've used as a lab.
Used a lot of ours?
Yeah.
Not much for me.
You can so there's a
The
website
CPU for you.
called greenalgorithms.com or something. I'll see if I can find it. And it gives you put in the GPU you've used and how many hours you've used it, and it'll give you your carbon emissions in terms of Paris-London flights. And it's pretty bad. It's GPUs are very resource heavy. It's why like large language models, there's some I mean they're useful, right? But it's what's called they're extremely resource intensive because they need data center level GPUs to work. And so instead of you writing an azimuthal average kind of function, something that's just out there, and you asking, I don't know, ChatGPT, Claude, whatever to use it, you've burned loads of fossil fuels to do that. And so it's a very kind of like not green way of computing. This is the website, Green Algorithms. And so you put in how long it was running, cores, the model, memory available, and it'll give you 3 months, how distance in passenger car, and Paris Dublin flights. Sorry, not Paris London. So
Start
something to
tracking
check
your
out.
GPU hours now.
Yeah, everyone should track their GPU hours and see how much energy they're consuming to do their research.
Well, we have a lot of GPU now.
Yeah,
It,
it's one
I've
hundred.
heard. Yeah, you guys have H100s. Can I use
It's
those, please?
wonderful.
Up to you, then.
Yeah,
Soon
AJ had
enough.
floated using the H100s for this chronograph design survey, just letting it go burr for like a weekend and getting 1,000 chronograph designs or something.
It- right now, it's the machine's off, basically. We don't
It's
even
funny.
access it, so.
Yeah.
There's time available. I don't think we're using it all the way, right? You even use it?
Rad.
On the Lila, right?
Yeah,
No, I haven't used Lila yet.
yeah.
I've
I'm-
tried it.
I'm going to once I start doing LOFIS simulations again. LOFIS is the one that takes a long time, not EFC.
ADEFC go burr. I'm surprised the Lofus takes a long time. For some
Well, it's
reason, I
because
just.
it's if you're assuming 500 hertz, it's 500 instances
Oh, I
per
see.
second of simulation you want to run. That's
Yeah,
why.
yeah. Okay, yeah, now I understand.
Jaren, also AJ has Gattaca 2 access now, and it's like 50% utilization with no wait times.
Amazing.
So
So yeah,
that could be
it's
our
a highly efficient algorithm plus bigger computer diplomacy equals future of research, essentially. Algorithmic differentiation is great. I highly recommend learning it. It's applicable to anywhere where you do math.
I have a question. What's the binary solution in your slide mean?
Sorry, what does it like what does it reach?
Binary solution. What you mean the binary solution? Is that
Oh
mean
yeah, sorry about that.
LOFIS.
So it means that the kind of so this is what I was talking about over here. And if we look at it in contrast to like oh wait, sorry, can you see my PowerPoint screen? I should have
yeah,
checked. Okay, sick.
Did If LFS
So
fall and it says
let's let's do
are
some
there,
live slide editing.
but
You
you just
see
want to
these
pause that.
values are kind of
What are you trying
gray,
to do? No, I'm trying to look at it.
whereas these values are only black and white. So it's much easier to make this kind of mask because you can deposit dots that are just don't let light through or let light through. And that's a very easy thing to do. The Black Silicon project that UA Sal's kind of working on in collab with AJ Riggs is a really, really good way of doing it, and how they did it for the Roman chronograph. Grayscale solutions, particularly accurate grayscale solutions, are super hard to make. And in fact, true grayscale has not really been demonstrated in a high contrast testbed. Instead, what they do is they deposit like little microdots to approximate a grayscale apodization. But it sort of like statistically represents grayscale. Like literally, if you squint at it, it looks grayscale, and then you open your eyes and then it doesn't. So they're much better, they're much easier to make, and they tend to have better core throughput, which is as important from a direct imaging perspective as telescope diameter. So that's what I mean by binary, is like basically manufacturable designs.
Have you ever played around with designing a PIA? Because PIAs technically give you grayscale just through phase.
Yeah, so no, the answer is no, because we thought about using Gaussian beamlets for it actually, because PIA has a high enough slope that it's not accurately represented by Fresnel diffraction. You need a higher fidelity diffraction simulation. What I have done is design a phase apodized pupil Lyot coronagraph, which is kind of the brainchild of Emil Poor, where you can do that one of two ways. You can either use a like a phase plate that's fixed, and we're interested in making those with metasurfaces, or you can basically pre-design a DM solution to have like a DM apodized Lyot coronagraph. And that follows very readily from the APLC design algorithmic differentiation. You only need to edit one line, um, maybe two. Going back here, um, see, I have this sort of constraint in the forward model that the input is real. If you constrain the input to be like if you take the input instead of apodization to be phase instead, then this instead of real of A becomes e to the I A, basically, as your input variable, and there is a corresponding adjoint operation for that. Um, and that's the only thing you need to change about this to make it design phase masks. And Keon's point is absolutely right. Phase masks give you grayscale phase apodization. Um, the kind of difficulty there is that pupil phase coronagraphs can only achieve high contrasts on a one-sided dark hole. They tank at like according to Emil Poor's design paper in like the 10 to the minus 5, 10 to the minus 6 is where you get limited to a two-sided dark hole. You just lose all your throughput trying to do a two-sided dark hole, and it really doesn't work very well. Um, so you can do really small inner working angle and very high throughput one-sided dark holes with a PAPLC.
Oh, I was talking about PIA CMCs.
Yeah, I know. We can't using the thing that I've just shown, you can't do PIAs, and I was like, but you
Okay.
can do PAPLCs.
Okay.
PIAs are different because there's a like a hybrid propagation physics engine that you need there. Kevin Fogarty has recently done some PIA design for
I
vortex
was thinking
coronagraphs.
about his presentation from Japan. That's why
Yeah,
I,
yeah.
yeah.
So if you use a differentiable ray tracer with Gaussian beamlet decomposition, you could nominally design what's called PIAs, but I don't know enough about how that design procedure works other than it involves some amount of ray tracing.
Cool. Thank you.
Yeah. Thanks for coming to the talk, everyone. Do you have any other questions, or is everyone going to IA lunch now?
I at least am.
Thank you.
Nice.
Thank you, Jaren. Thanks, Jaren.
Thanks. It's super
See
good
ya.
seeing you guys all again. Give Lena a good pat for me, please.